All right, I consented to being recorded. Is it,
All
all
right.
right?
Welcome, everyone. So today we're very happy to have Frederic Koehler. Frederic is a grad student at MIT. He's co-advised by Ankur Moitra and Elhanan Mosel, unless something changed from last time.
Nope, that's good. Yes,
That's
nice.
good, yeah. He works on kind of various things in learning theory, in particular a lot of stuff on graphical models, variational inference, kind of a presentational power of various things, various kind of classifiers, and so on and so forth. And today he'll tell us about learning half-spaces under Massart Noise. Take it away, Fred. Oh, I should maybe just say this is pretty kind of chill, so if you guys want to ask him a question, feel free to unmute yourself and ask a question.
Thanks, Andre. Yeah, I'll try to listen in case you guys ask questions, or let me know if, I'm not speaking loud enough or whatever. So this is a recent joint work with these three guys you can see right there. So Sitan, Ankur, and Morris, who's the lone non-MIT person, but currently visiting MIT, so really a MIT product. And yeah, this paper is about classification under misspecification. I'll explain what this means shortly. Let's see. There we go. Next slide. So I thought, this talk is basically going to have 6 parts. The good news is that the first few parts are longer than the last few. So if it feels like this talk is never going to end, it will end. And so just so that it's hopefully conceptually clear what's going on, first, I'm going to talk just about background, like what are all these models for half-space classification, including Massart Noise. Second, I'll talk about a new result we have, which is about proper learning of half-spaces with Massart Noise and distribution independent. The third point is an application to something called knowledge distillation, where we'll train a big classifier and use it to teach a little classifier. Fourth thing will be about basically the opposite of algorithms, will be about lower bounds, and it involves connections to this notion of evolvability in learning theory introduced by Valiant. Fifth thing is we'll go beyond just looking at half-spaces with Massart Noise and study a more difficult problem and give algorithm for that setting. And finally, we'll have some experiments and we'll discuss a bit connections to fairness. Okay, so let's get started. So first thing is, what is sort of like maybe the most classical model of learning a half space? So what's a half space? Like, we're going to have a bunch of points. They're going to be, we'll call the points X. They live in some, say, Euclidean space. And every point is labeled with a label Y, which is either +1 or -1. And that's going to be, basically the setup for the entire talk is we have these data points which are either labeled +1 or -1. What is typically going to differ between all of the models is how are X and Y related. So again, we're usually going to assume X, like we don't know anything about its distribution really, except maybe it's all of the X's have a reasonable norm. But we're going to have different levels of assumptions about the conditional law of Y given X. And so here's like the simplest possible thing, which I guess is called the realizable model, which is that there is some underlying half space W star. And the way a label is drawn is for every data point X, I look, am I on this side of the half space or am I on that side of the half space? And if I'm on this side, I label it +1. There's red triangles in the picture. And if I'm on the other side, I label it -1. And so it's like a classical, I guess, like pack learning model of half spaces. There are many algorithms to learn this. For example, if you have a so-called margin, you can use the perceptron algorithm, which I guess dates back all the way to the 50s. You can use more sophisticated techniques like linear programming if you don't have a margin. So suffice to say, it is a very classical and well understood model. So what can we do beyond this? Oh, yeah, and by the way, what happens in this model is like, in statistics, we could ask to recover the Stroop parameter W star. It doesn't make so much sense in this model because there could be many half spaces which generate the same label. So it's pretty much, it's not even information theoretically possible to recover W stars, no matter how much data we see. So really the goal is to be so-called like probably approximately correct. So we want to generate a half space which is very good at predicting the label Y given X. And so, for example, this W correctly separates all of the circles from the triangles, so it's getting a good accuracy. So people have come up with many attempts to make this model sort of more realistic. Perhaps the most famous, or one of the most famous, is the so-called random classification noise model. And as you can see, the generative model is very similar to before. We have a data point X. We look to see which side of the half space it's on. And you can think that we generate an idealized label Y star based on that, which is the same as before. But in real life with data, we often observe like there's no the data is not so-called linearly separable. So usually you cannot get 100% accuracy with any half space. And so to try to match that, what we can do is we can just add noise to the label. So the generative model is, first I see what side of the half space I'm on. Then with some probability eta, which is fixed for all points, I flip a coin, and if the coin is heads, I flip the sign. And so you can imagine, like compared to before, the picture of what the data looks like is kind of like this. It's like on one side there's mostly the triangles, on the other side there's mostly the circles, and on each side we have around the same fraction of incorrectly labeled points or differently labeled points, because eta is a universal constant through the entire model. So it's not so obvious that this model can be learned. Like you cannot just use linear programming, but there was a series of works in the 90s, including this one by Bylander, which sort of requires margin, this Bloomfries, Kannan, Vimpala, and Cohen papers, and they really solved this problem. So we now know how to learn a half space with RCN noise. So this could be the end of the story, but it's not. So in many applications, we think that this assumption that everyone is flipping coins and the coins all have the same weight is not so realistic. So what can we do to make the model more general and perhaps even more realistic? One thing is the so-called agnostic learning model. And in some sense, this is the most satisfying, because what really happens is, we have data points like X maybe are featured vectors corresponding to people. And then we might give them a survey. They respond to the survey in some way. But for example, they may not always tell us the true answer. Sometimes people lie on surveys. People have a very complex decision-making process possibly for how they generate the label Y. And we really don't know all the details of how people's brains work. So it seems like a reasonable thing to say, okay, well, there's X, there's Y, which is plus minus one labeled random variable. It's correlated with X, but I'm just not going to assume anything about the joint distribution of the data point and the label. And so if I'm going to have that set up, there's no sense that there is a true half space, but there is still a meaningful learning goal, which is basically, I want to have the situation that if there exists a half space, which is pretty good at labeling the data, I want to be able to find a half space, which is roughly as good. So that's the agnostic learning objective. And so a little more formally, we would define opt as like over all half spaces, which are parameterized by the weight and bias, what's the lowest error you can get? And our goal is to find a predictor H, usually a half space itself, such that the probability that H is incorrect is only slightly bigger than opt. So it's basically as good as the best half space. And so that would be a very nice model. The problem is we can't find algorithms that actually work in this model without making further assumptions. So there's a series of papers on this problem. And maybe the most recent is this paper by Daniele, which showed under some cryptographic assumptions, you can't even learn this improperly. So if I let you fit something more powerful than a half space, could be totally uninterpretable, you still can't do it. And also he showed that you cannot even do it weakly, so you can't even do like a little bit better than 50% accuracy. Like that is, both of those things are not possible to do. So basically it's, yeah, there's no hope for coming up for algorithms for this model. And so this kind of leads us to this trade-off.
Hey, Fred.
Yeah.
Before you continue, so Ainesh has a question for, I guess, the random noise model. Does it matter that the flips are IID?
Yes, it matters that the flips are IID, yes.
And Also, I have a quick question. So
Yeah.
is the Danieli paper the one that uses like the Feige-like assumptions, like the random set-like
Yes, yes,
assumptions?
they use a random set assumption. Yes. Yeah, so there, that itself has some interesting history where I guess the first assumption was not quite right, but has been fixed. Yeah, okay, so let's keep going. So based on what we discussed so far, there's sort of a spectrum of models. There's the really simple model, which is no noise, which we are very happy with in theory, but is maybe not very realistic. There's RCN, which is a little more realistic, but still pretty naive. And then all the other on the other side, we have agnostic, which is like potentially very realistic in the sense that it captures many situations, but also maybe not realistic in the sense that it captures very like maybe like the examples which are hard or unnatural, like you would never see them in real life. And so we sort of have this Goldilocks problem, like we kind of like to get in the middle, like we would like the most general model we can learn that's not just completely impossible. And yeah, by the way, there's this other box, which is GLMs, that stands for Generalized Linear Model. This is something that we're going to get to a lot more at the end of the talk. But basically, in random classification noise, your expectation of y given x is given by a threshold unit. So it's like -1, then all of a sudden it jumps to 1. GLM is a more general model where captures like logistic regression, where the law of y given x has, it's linear, and then you have a link function, which is usually assumed to be Lipschitz. So basically, that's a more general class of models than RCN, which are also interesting. But they still have some limitations, like your noise level can only depend on x in a very particular way, which is also related to expectation y given x. So this talk is mostly about this model called Massart noise, which I will define in the next slide. And it really sits on the boundary between computationally tractable and computationally intractable. So here is a diagram of the Massart generative model. So it's kind of a non-parametric model in the sense that there's going to be a per x noise rate, which we'll call eta of x. And we really don't make any assumption on that function. Like it could be totally crazy, not even continuous. But the assumption we do make is that the noise rate is upper bounded by eta. So when we write eta without the x, that's the upper bound. And as you can see, it's like the RCN. We first have a point, we generate, I guess, a clean label. And then with probability eta of x, we flip the label. So maybe, for example, like, I think in many situations in real life, eta of x could be a complicated function. So maybe one example is if you are taking a poll online. I was asked recently by YouTube, like, how old am I? And I know that Google has like a ton of data about me because that's what they do. So I know that x is a very rich random vector that contains like everything about my interests and so on. So but then you can imagine other people, like they're smarter than me, like they don't use Google, so that Google doesn't know everything about them. So for them, the noise rate in predicting the age is going to be very different than for me, who is giving away all his personal information. So, and unlike in a GLM, it's not really like the noise rate is not really related. I mean, it's probably a factor of a lot of things that are different from the thing we're trying to predict, which is the age. Yeah, there are other examples of this, which maybe we'll discuss later, but that's the model. Yeah, so you can sort of view this model from RCN perspective or agnostic perspective. So from the RCN perspective, it's like, it actually seems like a pretty benign model because it's like I have RCN with a flip parameter eta, and the adversary can only make the seemingly helpful change that at some points x, it can reduce the amount of noise. So it's just, I see y star more often than I see negative y star under RCN, which is, it's given that phrasing, it's surprising that this model has been so hard. But yeah, it turns out actually if you use RCN algorithms, they just totally break in this model. So it's actually a pretty serious adversary. The other interpretation, which makes it sound much harder, is it's like agnostic in the sense that an adversary has pretty much arbitrary control over some portion of the data, but that fraction of the data is random. So basically, for every data point, I flip a coin that's eta biased, and if that coin is heads, the adversary can just change the label to whatever. there's like a small technical point that if you know about sort of robust statistics or other settings with adversaries, there's a difference between an oblivious adversary and an adaptive adversary. These interpretations are the same when you consider oblivious adversaries, but all of the algorithms we'll talk about in this talk, they can be adapted to adaptive adversaries as well. So if you care about that difference, just know that you can handle that as well. Yeah, so I guess the earliest reference to this model is apparently this paper by Sloan in 1988. But Cohen's paper about learning half spaces with RCN also posed this as an interesting open question. Okay, so let me next talk about sort of state of the art before our work. So actually, there's been a lot of interesting work on this model. So the main line of work has actually been on, I'm going to make a distributional assumption on X. So for example, it would make sense, to say that my X are drawn from Gaussian distribution, log concave measure, uniform on sphere, which means we're not dealing with the general case, but could potentially make the problem more tractable. Yeah, two of those papers are by people in Nina Balkin's group. Yeah, several other interesting papers, most recent by DKTZ. So in comparison, people didn't really study the general case that much until recently, or at least they didn't publish about it. And so recently there was this very nice work by Diakonikolas, Kouliakis, and Samos. And what they showed is that they could not learn a half-space classifier in this model, but they could learn an improper sort of decision tree structured model. And it doesn't achieve, like, the normal guarantee you would ask for is op plus epsilon, which is basically give me a half space that's as good as the best possible half space. What they can do is they can achieve error eta plus epsilon. So the thing to think about is opt is always at most eta. Opt is basically corresponds to how much is the average noise level. Eta is the upper bound on the noise level. So they can only get eta plus epsilon. But yeah, that's much, much better than what we knew before, which is almost nothing. Okay, and then they pose these open questions. One is, obviously from this context, we want to know, can we get op plus epsilon? So by the way, in the distributional assumption setting, pretty much you always get op plus epsilon. So it's not like it's always impossible to do this. And the second question they ask is, can we do it properly? So basically, as you take epsilon smaller, their classifier becomes more and more complicated. But we know there's a very simple half space which does really well in this model. So those were both interesting questions. And we're pretty much going to answer both of them in this talk. Okay, so first thing I'll talk about is the proper learning aspect. By the way, let me just check the time. Cool. Yeah, so we're going to improve their improper learner to a proper learner.
Hey, Fred, sorry, before you continue, so what's the dependence in the polytime on the gap of, I guess, eta from 1/2 and epsilon?
Oh, yeah. So basically, it's polynomial in 1 over 1/2 minus eta. So as you take eta closer to 1/2, it takes more into it. I forget, was there another question?
But it's poly in both, right?
Yeah, it's polynomial in all those parameters.
And the other question is Ainesh. He asks, what is the least restrictive distribution setting in which algorithms work?
Yeah, if you look at the DKTZ paper, they have a sort of anti-concentration assumption, which is kind of general. We'll actually talk more about in which settings you can and cannot do it later. So hopefully that will also be interesting. So there's some settings which seem relatively benign, but turns out you cannot do it. It's a little complicated. Okay. Yeah, so let's keep going. Let me tell you about properly learning a Massart half space. Again, this is in the distribution independent setting. And so, like, what is one of our favorite tools in machine learning? It's like, we want to optimize 0-1 loss. It's not convex. If you do gradient descent on that, it really doesn't work. So, like, oftentimes we try to come up with a convex surrogate loss. And this seems really relevant to learning half spaces in Massart because it actually does work very well for half spaces under RCN. And so actually, this is, again, a special case of a more general theory for so-called generalized linear models. And this theory is actually called it's like the matching loss theory, because there's a really nice, simple convex surrogate you can use, which is going to succeed. In particular, for RCN half spaces, the loss looks like this. So it's basically, it punishes you a lot for, like, that's the x bigger than 0. It punishes you a lot for having the wrong label. It also rewards you a little bit for having the correct label. So it's kind of like hinge loss, but hinge loss would be 0 in the negative axis, and this one is going negative. And so we know this works in the RCN setting. Another technical thing is you might want to smooth this function near the origin by a very small amount, but this won't be super important to us in this talk. Okay, so the most obvious thing is we know this works for RCN. It's like a nice convex optimization program. Why not try it for Massart? And so a nice theorem that is proved in this GGT paper is actually, not only does that not work, there's just no way that this is going to work. Like, it's not just you can try a different convex loss L, and like maybe that one in particular is not good, but like if I change hinge loss in a different way or use logistic loss, like none of those are going to work, in the sense they're not going to get anywhere near error eta plus epsilon. And like the last thing is like, yeah, they show this even with a margin assumption. So for RCN, if you have margin versus if you don't have margin, actually affects this. But for Massart, even with margin, it just doesn't work. So that's pretty discouraging, because like that's one of our main techniques. So how could we get around this is basically we have another, I guess, bullet in the gun, which is we really like zero-sum games. So how could we try to use that to make the problem better? And so it's not so obvious. So first, what I'm going to tell you about is like an idealized zero-sum game. So what do I mean idealized is we're not actually going to be able to solve this zero-sum game. But if we could, we would have really nice results. And so this is the zero-sum game. Let me tell you what do these, well, okay, it's a game between two players. So this W is the classifier, and the max is a special kind of discriminator who is basically, they want to show that this W is not the true W star. And what are C and L? So the discriminator gets to reweight the data distribution in an arbitrary way. So you should think that C is like it's like a change of measure. So like we're familiar in like boosting and so on. But it's only allowed to depend on X and not Y, which is important because if it can depend on Y, this is basically an arbitrary function. So it can only reweight the distribution over X. And the reason this is supernatural is Massart noise is an assumption on Y given X, so the so-called concept. And so if I reweight the distribution on X in any way, I don't go outside of the Massart half-space model, which is not true, say, for agnostic. Like agnostic, if I reweight the distribution, I might totally kill the accuracy of the optimal classifier. But we always stay Massart if we do this kind of reweighting. What's L? It's pretty much the same loss from before. Before there was like a little thing about smoothing. We're not going to do any smoothing, so it's actually exactly equal to this function that people are familiar from neural nets called the leaky ReLU, because it looks like ReLU, but it's invertible, which we call leaky ReLU. Yeah, it comes from this matching loss theory in some sense that you could predict this is the correct loss to use, and it's also used in the DGT work. Okay, and here's an important fact, which I won't give a full proof of right now, is that if we could solve this game, so that means we find the W which is optimal for the min player, we would actually have just totally solved the problem. So we'll achieve error opt, even better than eta. So the proof of this, well, yeah, it's actually not entirely trivial. So I think it will sort of be clear once I explain all the other results. You can go back and think about this, like, why is this true? But it kind of makes sense because the max player has a lot of power. They can pretty much just reweight the distribution to be on points you're doing really badly on, that the true W does well on. So it's kind of intuitive. Okay, so what's wrong with that? The problem is like the min player is really happy because look at this expectation CXL, that expression, the innermost expression is a convex function of W. Now we're taking a maximum of convex functions, so that's still convex. So this is really great from the min player's perspective because they're actually just trying to minimize a convex function. So it's super good. From the max player's perspective, it's totally bad because, well, first of all, it's obviously a big computational problem to try to pick the best reweighting of all possible reweighting. There's no structure to that. Secondly, like you can imagine if I pick a reweighting that's like very spiky, I may, like I may need to take a lot of data to estimate this expectation. So basically, you need to do importance sampling. So yeah, so it's totally hopeless, unfortunately, to actually play the max player's optimal response. So what can we do? Oh, basically, we just say, okay, the max player is not actually allowed to consider all reweightings of the distribution. We only allow them to consider very specialized reweightings of the measure. And you can see in this picture over here, the things we restrict them to are like, we're going to call them slabs. So the C of X is actually dependent on the W that the min player plays. And a slab is just you look at the decision boundary of the half space and you thicken it by R. So that means you look at all of the points where the dot product is at most R in absolute value. And that's the only sets that the max player gets to play. And so, that's specified by a one-dimensional family of parameters, so you can efficiently optimize that. And so, yeah, even though we greatly restricted the power of the max player, we still get something out of this minimax game. So it turns out that we're going to prove gradient descent for W. It doesn't give an opt learner, but it gives an eta plus epsilon learner. There's the usual, technical details. The expectation cannot evaluate it, so we estimate it over data. Also, it doesn't really make sense if you consider an R such that there are no points in the slab. So R is actually only allowed to range over slabs which have a reasonable number of points in them. So there's kind of minor technical details. Another thing is this doesn't quite work in the non-margin case. So gradient descent is, among other things, not so good. And if you try to do linear programming with gradient descent, you have a problem. So there is a different way to do this for the non-margin case, which is related. I think I'm not going to explain it in this talk, but it's in the paper. So it's, in particular, the restriction is a bit more complicated than just looking at slabs. Okay. Yeah, so I told you the result, the only mystery is why is it true? So I'll try to explain that, and I'll give a pretty much a complete proof. You can see these are kind of Franken slides. I copied and pasted some different slide sets. So here we are going to use an important idea from the DGT paper. So basically, I'm going to tell you more or less how their algorithm works. And so what they do is they minimize the leaky ReLU loss, the same one that we've been talking about. And we know that this is not going to give a proper learner, but it gives something still useful. So it gives a half space which is good on a subset of the data, which is actually an anti-slab. So you look at points that are far from the decision boundary. And actually, if you look at like the 0-1 loss and leaky ReLU, like you'll notice that like leaky ReLU looks kind of like the integral of the 0-1 loss, although not quite. And in particular, it weights the points that are far from the decision boundary a lot more than those that are close. This kind of sounds intuitively reasonable. And yeah, since I proved that, they can find a good classifier on part of the region and then forget about that region, repeat this algorithm several times, and it builds a big lopsided decision tree, which is good at classifying points. And so what's the key insight to get a proper learner, or one of them, is if we want to get a proper learner, it's obviously bad if we are good on only some points and not others. And what we would really like to do is actually, we want to get a gradient. So we should really focus in on the points that we're doing badly on. So that's why instead of looking at anti-slabs, we look at slabs. Okay. First of all, let me tell you, like, what is leaky ReLU exactly? It's exactly this expression. So it's 1 minus lambda z for z positive, lambda z for z negative. It looks like that. I'm going to talk about the leaky Rayleigh loss. It's just the expectation of the leaky Rayleigh of negative y w dot x. And yeah, like I said, I'm going to just assume a margin. We're going to have polynomial dependence on the 1 over gamma. So this will, I mean, this is useful in particular because the resulting algorithm is much simpler and more practical. Okay, so let me tell you this lemma, which is in the DGT paper. Turns out, so basically, you can imagine we're doing optimization. We want to get something that's good like W star. We have a loss. We should figure out how small is the loss for W star. And so we get this upper bound, which is to say that basically says it's negative. And not only is it negative, but if you have a margin, it's significantly negative. And here, lambda is going to be this parameter, which is like eta plus epsilon. So we need that also for the upper bound to be not 0. Turns out this is, you pretty much just write out the definition of everything, and it's immediate. So first, you can rewrite the leaky Rayleigh in this way. And the reason that was really good is because when you have an indicator and you take expectation, you get a probability. So if we plug in that definition of leaky Rayleigh and then use the law of total expectation over x, we just get this expression like L of lambda is equal to, is basically this inner expression is like the 0, 1 loss for this particular point minus lambda, and it's weighted by w star dot x, which is like the distance from decision boundary. So now to prove it, we just observe like that probability is exactly eta of x. It's at most eta, so most lambda. In particular, this number is always negative. So using that, we get the negative upper bound. Second key lemma, we need to understand what happens for the other w's that are not w star. So we know for w star, the loss is negative. Actually, yeah, maybe I should say like that's also true. Like we just proved a general result for Massart noise model. So I can reweight the measure on x in any way, and the loss is still negative. So here now what we're going to do is we're going to look at a w which has a big error, so it's not like w star. And we're going to show that there's some slab where the loss is positive. And so that's going to mean we're going to see like w has a positive loss, w star has a negative loss, and that's going to allow us to make progress. So SWR is just notation for a slab. Yeah, so just to sort of reiterate, basically, we're going to set up this game. You're going to be paying a lot of loss for W compared to what you would have for W star whenever your 0, 1 loss is too big. So if we are doing well in the game, that means we'll start to get negative loss. And then using the contrapositive of the lemma, it means our error can't be bigger than lambda. So that's the high level. The proof is basically just uses this idea that 0, 1 loss and leaky Rayleigh loss, they are sort of integral of leaky Rayleigh looks kind of like the integral of 0, 1 loss. It's also used in all of the previous papers with the leaky Rayleigh. So the matching loss papers and also the DGT's paper. To prove this lemma, so recall, we want to show W has bad 0, 1 loss. There's a slab where its leaky Rayleigh loss is positive. So to prove it, let's do contradiction. So there's on every slab, our leaky Rayleigh loss is negative, even though our 0, 1 loss is bad. So just writing that out, we get this expression. Now we remember it's a really good idea to write x as the integral of 1. So let's just do that and plug it in. So now we get this expression. Perhaps it is not yet very clear why this is useful. So let me just rewrite this a couple times. So, okay, first of all, because I have an integral, by the way, like if the integral is negative, I obviously know that there's some place where the integrand is negative. So first I'll do that. That's good because we have this indicator that looks kind of like a slab already. So by doing that, we get that for every r, there's S of r so that the integrand is negative. Now we can start to make more sense of this expression. So we have this indicator. We can move to the conditional expectation just by dividing by the probability you're in this region between S of R and R. And now we get something that actually makes sense. So we get lambda is an upper bound on your 0, 1 loss in this region where, so this is like, it's not a slab, it's not an anti-slab, it's like an annulus. So you look at points that are not within S of R of the decision boundary, but also not further than R. And so why is that useful is by putting together a bunch of those regions, you can actually just cover the entire space. So basically how to think about this is first I take R is equal to 1, because that's the biggest possible value of W.x. Then I'll get some smaller S of R, like 0.5, and I know 0, 1 loss is good in that entire region. Now just keep doing that over and over. Perhaps you might have to do it uncountably many times, but definitely at the end, you'll get that overall your 0, 1 loss has to be at most lambda, because on all of those regions, it's better, it's smaller than lambda. And so that gives a contradiction. So yeah, that's, yeah, you can kind of think it's kind of like a thought experiment where you keep filtering anti-slabs, and the important thing is you always look along the same direction so that they're easy to combine. Okay, and so basically, what's the point? We know from the first lemma, W star has negative loss, significantly negative loss, and so every time that we get a positive loss for W, we get that the loss, the leaky Rayleigh loss of W, is positive. It's minus something that's very negative. So the gap in performance between W and W star is very big. And those are convex losses. So what can I say is, this is a very general and useful tool for minimax games, is the max player is able to keep finding convex losses such that my W is very bad compared to some fixed W star. And the thing is, like, if you know about the different analyses of gradient descent, one of them actually proves that even if the loss function is changing at every step, you still cannot have this situation. So like, basically gradient descent is low regret in the sense that if no matter what sequence of convex losses you give me, I'm not going to do too much worse by playing the gradient descent iterates than I would by fixing the optimal weight W star. And so basically, as long as I'm getting big 0, 1 loss, I'm getting big regret. Gradient descent cannot get big regret for a long time. It would violate the guarantee for gradient descent. So sort of proof by contradiction, at some point your 0, 1 loss actually has to become good. So yeah, basically at some point you'll get, on all of these slabs, the loss is negative. Then by lemma 2, you get eta plus epsilon 0, 1 loss. And that completes the proof for the proper learner. Yeah, I'll go on to the next part. So yeah, what is knowledge distillation? So we're taking this terminology, I think it's mostly used in the neural nets literature, actually. Like I said before, it's like we want to train a big classifier and somehow use that to generate a little classifier, and it's actually going to work better than if we just train the little classifier itself, which is definitely not true in all settings, and could perhaps be counterintuitive that would even make sense. But it's not so crazy because we know it actually works sometimes in practice. So like if you want to deploy a big neural net to a cell phone, it would use a lot of energy to do inference, but we can do knowledge distillation, also called model compression, get a smaller neural network, and that is more energy efficient at inference time. Okay, so let me tell you. Yeah.
Before you continue, Ines just asked if you can redo the result without the margin, or if if the margin is essential.
Yeah. So, right. Basically, what happens is, maybe I can go back to all the way to the minimax game. Oops. Sorry about this. Yeah, so what happens when there's no margin? We do also have an algorithm that works in that case. Basically, it's the same idea that we're going to look at the general minimax formulation, and we're going to restrict it so it's actually possible to compute the optimal play for the max player. In this case, instead of looking at slabs, well, you can sort of imagine that one of the issues here is that when all the points are very close to the margin, or sorry, very close to the decision boundary, all of the numbers in the expectation could be very small, and then it's very hard to estimate small numbers. And so the fix is going to be something like you're going to, like another thing you might have noticed is I talked about this general change of measure C, but so far I always used it to restrict to a set. But this is actually not the case for the non-margin case. We're actually going to pick a C which rescales, which emphasizes points close to the decision boundary. So it's going to be, C is going to be a really big number when you're close to the decision boundary. And that's going to fix this issue with the small numbers. You also need to do something called outlier removal, which people basically in the RCN half space literature, people already figured out how to deal with some of these issues. So we can actually just use the, we can use this same so-called outlier removal procedure to make sure that various statistics concentrate well. The other thing is, yeah, the gradient descent is not so good. So we'll use a cutting plane method. So basically think that we'll use ellipsoid method for W or Vaidia's algorithm. And for R, instead of for the max player, we consider a more general C.
Is it the case that you still get a proper learner when there's no margin?
Yeah. So by running basically ellipsoid for W and this other more complicated strategy for max player, we do get a proper learner for the no margin case. So instead, it depends on the bit complexity, because in linear programming, we always depend on bit complexity.
Sure. Yeah. Is it okay to think about the C sub x or like C of x as a probability distribution that you are then reweighting?
Yeah. So that is definitely the case. So C is, we can think as a change of measure, so reweighting. Another trick that appears only in the non-margin case is the Leaky-Rayleigh loss is homogeneous. So you can actually put the C of x inside of L, and the expectation is unchanged. And so that's really useful, because then basically it's like a variance reduction trick. Like instead of viewing it as a change of measure, which requires importance sampling, we view it as a rescaling of the data, which doesn't require importance sampling. So yeah, there's I guess several tricks involved in the non-margin case.
I see. And why is importance sampling bad? Because you could do it pretty quickly, right?
Yeah, so for the slabs, we can do it very quickly, but for the C of x for the non-margin case is very spiky near the decision boundary, so then it will not be good for importance sampling.
Thanks. Yeah. Thanks.
Yeah, thanks. Cool. So let me go on to knowledge distillation. Like I said, we want to train a big classifier, use it to make a good small classifier. So what should you think is, basically imagine we have a Massart half-space model like before, and opt is a lot smaller than eta. Then we're not so happy right now with our proper learner in the sense that it doesn't get all the way to opt. But there's actually an easy way to help it, which is to give it access to a teacher H, which is, it could be any sort of improper learner. So it could be a huge decision tree, it could be neural network, could be a huge linear model. So if we give our proper learning algorithm additional access to a classifier H that does better than eta, so maybe it's halfway between opt and eta, or it's very close to opt, we can actually modify our proper learner to extract a half space which has equally good performance. Oh, up to plus epsilon, and as you take epsilon smaller, we run longer. So it's black box in the sense we don't care about the structure of the teacher H. Although we do, you cannot, we do require to look at additional samples from the distribution, but that's the only other thing you need. Yeah, so it turns out, yeah, this follows almost immediately from the previous result. is not obvious. So again, we're going to think about this min-max framework. And the trick is basically when I have a teacher, I can actually do a much better job of coming up with reweighting C of X. So imagine I have a teacher H, which has really good accuracy. I have a student half-space W, which doesn't have very good accuracy. How should we try to improve the student W? Well, there's no point looking at examples where H and W agree because, like even the teacher might be wrong on some of those examples. We don't have a good hint as to how to correct W. So instead, focus on the examples where they disagree. And because the teacher is better than the student, that means like the teacher's accuracy is much higher than the student's accuracy on the sets where they disagree. And in particular, the student actually does worse than 50% because if they did better than 50%, that means they're better than the teacher. So this means we can find this set where the student is doing extremely bad, which I guess we'll call S. I have an illustration over there. So we sort of have a nonlinear classifier, and we have the proper half space W, and S is the region where they disagree. And so the first step is we just restrict to S. And now this is really great because all of a sudden, like the student W is like really bad on this region. So basically, we can just run the proper learner because like the student gets above 50% error. Our proper learner can find a half space which has less than 50% error. Actually, we just run a single step of the proper learner. It finds a slab where you have bad leaky ReLU loss, and you can do a gradient step based on that. So yeah, except for restricting to the disagreement set, it's just exactly the same as before. And what you see is that by doing this, use gradient descent for the min player, we actually get to train the proper half space W to be just as good as the teacher H. And so this has a few cute applications. I'll tell you one. So we have many results for agnostic learning, which are only improper. So this is a famous one. So suppose you want to learn a half space agnostically. It's hard in general, but let's do it. Let's assume X is uniform over the hypercube. So that's good because we can sort of use Fourier analysis tools. So then KKMS, Kalai, Clivin, Mansour, and Servideo, they prove you can get O plus epsilon for any fixed epsilon in polynomial time. But so far, no one knows how to make this proper. It's sort of an open problem. And in particular, there's no way to just, in the agnostic setting, we don't know any way to take this huge improper learner and convert it to a good proper learner, even though we know there is a good half space. Yeah, but magically, if we're in Massart, like we have this super big hammer, which is this distillation theorem. So like first we just use KKMS. I mean, agnostic is a generalization of Massart, so obviously the theorem applies. It basically does linear regression on a huge polynomial basis, generates some extremely complicated classifier. And then we just apply the distillation theorem, use a few more samples, and we'll just get a half space, which is equally good. And so this is the first proper learner. Well, there wasn't really anything known about proper learning for this setting, uniform on the hypercube before. So yeah, interesting because we knew about uniform on the sphere, and hypercube doesn't look so different, but we had nothing for this before. And here the previous algorithm we just presented got eta plus epsilon. Now using the KKMS result, we can get all the way to O plus epsilon. And there's many other applications of this. Just basically, we use results from agnostic learning that cannot be made proper as far as we know. And in the Massart setting, we get a bunch of new results. So for disjunctions, you get a similar result, but with a much better dependence. Okay. And so this leads to an obvious question, which is like, I just talked like, yeah, like we only know how to get eta, like we'd really like to get opt. Well, we can get help from a teacher, then we can get better than eta. But it could be, as in many cases, like the teacher is not helpful. Like you can actually just train your half space without access to that additional oracle. So yeah, we really need to answer this question, like, can you just get O plus epsilon just based off the, efficiently and just using samples from the model? As it turns out, the answer is no. The key to understanding why actually involves connections to this theory of evolvable algorithms. So I'm not going to define fully the evolutionary model because it turns out it has a useful characterization that's much easier to state. But the original definition of the model is basically something like this. You start with, say we want to learn half space. We start with a half space W. We come up with a proposal set of like possible W we might want to evolve to. And we look at how good they all do in the 0-1 loss. And basically, if one of them does much better than the current W, we will evolve to that. So it's a little more complicated than this, but basically that's what the evolutionary model is about. And so Feldman showed that the evolutionary model is equivalent to the correlation statistical query model called CSQ. So in one direction, this is obvious because, okay, so CSQ means I get to query expectation f of x, y for any f of x. 0-1 loss is of this form. Because like basically you can count the number of examples where you're right minus the number where you're wrong, and that's exactly a CSQ query. So it's clear evolutionary algorithms can fit CSQ. In the opposite direction, is Feldman showed you can take a CSQ algorithm and make it into an evolutionary one. So they're actually equivalent. And now, like, what does this have to do with Massart half-spaces? Turns out it actually has a lot to do with Massart half-spaces. So let's look at a CSQ under a Massart model. So that's the left-hand side of this equation. We can use the law of total expectation for y given x. What do we get? We get expectation of y given x is the true sign w star dot x. So over here. And then there's this noise level, which is 1 minus 2 eta x. And so what happened is I started with my Massart distribution. But if I make a CSQ query, it's equal in expectation to this other query. This query is in a noiseless half-space model. And the only change is this factor, which only depends on x. So again, we think of this as a reweighting of the distribution. And it's a relatively benign reweighting in that this number cannot be very small or very large, because eta is bounded away from 1/2. So that seems like an extremely useful fact for coming up with learning algorithms. So let's do a thought experiment. Suppose we knew a distribution independent way to learn half spaces. It makes CSQ queries, and it doesn't have to deal with noise. Now, like what I just said is, well, if we have Massart, like the real setting we're in is Massart, but if we only make CSQ queries, it just looks like a no noise half space model with a slightly different distribution of x. So I can actually just run that CSQ algorithm, which works when there's no noise, and I would be able to learn the half space under Massart noise. And because there is a change of distribution, but the distributions are like, their densities are bounded with respect to each other. So if you get a plus epsilon on one, you'll pretty much get a plus epsilon on the other. So actually, this would just totally solve the problem if this were the case. So super relevant result, Feldman proved that there is no distribution independent way to learn half spaces. And so once you know all of this, you can open up his proof and realize you can prove an even stronger lower bound, which, so I let you make SQ queries. So I can query basically the expectation of any function of x and y. And I can tell you the distribution over x is uniform on the hypercube, like we considered before. Pretty much what I'm saying is you open up his argument, it still works for proving the stronger result. And so we just get that there's no a plus epsilon half-space learner making SQ queries. And like usual, SQ captures all of our natural approaches based off gradient descent on convex losses. So this seems to more or less rule out the possibility of getting an efficient learner. Oh yeah, so another thing that's interesting is the second bullet point. So I told you this whole thought experiment, it seemed pretty useless in some sense because there's no CSQ algorithm for learning half spaces. But actually, you can just do this thought experiment for specific distributions. And you actually realize that people they almost made this connection. So one of the algorithms for learning Massart half spaces over the sphere is basically you do Langevin dynamics on the 0-1 loss. If you think about that, that pretty much instantly fits into the evolutionary algorithm framework, because actually all of the steps can be done just by looking at 0-1 losses. Yeah, so their thing is already pretty much a CSQ half-space learner. So pretty much everything is, and when you realize that, you actually realize that people studied a very similar problem before. In 2010, there's this paper by Kinnaid, Vaughn, and Valiant. Actually, this VLC17 result, it really can just be thought is a very similar algorithm to the one in the KVV paper, and they proved a stronger result for it. So there were some unnoticed connections between these two fields where people actually studied very similar things. Okay, I think I've used a lot of the time. So there's this last section, which I guess basically depending on how much time we have, I'll either blast through it or not, and then there's some experiments. So what do you think, Andre?
I think whichever one you feel is more interesting, go for that one.
I mean, this section is not very long because I anticipated I'll run out of time. But I also think the experiments are interesting. So maybe
if you also want to run over for a little bit, like it's a reading group, like it's
yeah,
not
okay.
that much of an
Let me.
issue.
Yeah. I was already planning to blast through this section because. So let me just try to give you a little idea of what's happening here. Let me at least tell you the model. So we can learn actually this more complicated model where expectation of y given x is instead of a threshold unit, I get to use an arbitrary nonlinearity sigma, which let's assume it's Lipschitz, it's monotone, and it's odd. So it treats negative and plus symmetrically. So we know how to learn this if this is exactly the model. So that's called learning a generalized linear model. In the probabilistic concept model, we know how to do it. So then we consider two more difficult versions. One is like the Massart setting, I let you make helpful changes. So you can move expectation of y given x away from 0, which means you improve the signal to noise ratio. We'll call that 0 misspecified GLM. Then we thought that was not hard enough, so we considered an even more difficult model. You're actually allowed to flip the sign of expectation y given x. So you can basically move expectation y given x by an arbitrary function bounded in L infinity norm by zeta, which is interesting because you can plant like the opposite of the original signal in some parts of the space. It's actually kind of like agnostic learning if you think about it. But yeah, let me not dwell on that. So the model looks like this. Basically, we prove a generalization of this eta plus epsilon learning guarantee for this setting. So how to interpret this? We consider arbitrary zeta. We'll get two terms on the right-hand side. One is the error of W star under the clean GLM model. So no adversary involved. And so that's analogous to eta. The other thing is we added this sort of misspecification term. There's definitely nothing you can do to get below zeta because of the hardness of agnostic learning. So we also need to pay the misspecification cost. So those two terms together are generalize the notion of eta, and we can find a hypothesis H in poly runtime, which gets an error upper bounded by this generalized eta plus epsilon. So it's unfortunately only proper right now when zeta equals 0. It's a little unclear. You can get a similar-ish guarantee maybe when zeta is bigger than 0. It's not totally clear what is and is not possible for proper learning in the misspecified case. Let me not dwell on that. Yeah, maybe I won't go into all the detail of this. Basically, we wanted to try to use a similar approach to the improper learner from DGT. Doesn't quite work because basically you'll get this anti-slab and you'll have a good guarantee for your error of your half space on the anti-slab, but it's actually not the right one. So what you get is R is the anti-slab. Its error is upper bounded by how much error you wanted to make on the entire space. So then if you think that R is like R might be a region where the W star actually is very accurate. In that case, it's not acceptable for us to get something that's like, say overall accuracy is like 60%. And on R, the true half space gets 99%. It's not going to be acceptable if we look at R and we only give you a 60% guarantee because, yeah, we need to be like, then, on the complement of R, actually, you cannot even get close to 60%. So it's not going to work. You need to be competitive on each region. So in their approach, you freeze the region R after one step of this Wiki-ReLU training and anti-slab extraction. It's not going to work for us. You can sort of just try to do the same thing, but you keep recursing on R. So basically, you'll split the space into two and recurse both on the anti-slab R and the slab R complement. It sort of works, except it runs in exponential time because you keep splitting the space in half. So it doesn't work. Then, yeah, we think about it like, oh, gradient descent, like we're trying to do gradient descent in functional space. What happens? Our function got too complicated. We need to add a projection step. So basically what we do is we actually do just keep generating a bunch of regions, but later after we do that, we look to see if two regions are very similar and then we'll merge them. And there's a very careful way to do this so that the number of regions stays bounded. Then it's kind of interesting. You don't get a simple decision tree. You get this kind of complicated like DAG or threshold circuit structure. Yeah, so it's a little complicated, but that's the high level. Okay, let me tell you the experiment. I think this is kind of interesting. I'll skip the synthetic experiment. Let me tell you about the experiment on sort of real data. So the UCI adult data set is it's census data from 1994. You are given a bunch of features like gender, education. You want to predict if the income is above or below 50K for a person. That's a classic data set. It's very popular in fairness, actually. And so we consider in this experiment where we look at a target group G. So let's say a woman making over 50K. And we're going to modify the training data by adding noise outside the target group. So we actually don't affect the target group, but we add noise everywhere else. And what happens when you do this, and we use a standard classifier like logistic regression. And yeah, there's some motivation. I mean, there's many settings where different groups have different, I mean, I gave an example before. In the interest of time, let me not give other examples of situations where the noise varies between groups. And so when we do this experiment, what we see is this blue curve here is logistic regression. And the green curve is the algorithm we proposed for properly learning Massart half-spaces. So it's this slab-based algorithm. What we see is that all of these algorithms have a similar overall accuracy, but as you inject noise outside of the target group, for logistic regression, the accuracy in the target group just totally plummets. So once we add like 20% noise outside the target group, inside the target group, we didn't actually do anything, but logistic regression sort of, it creates this bias where it just assumes that everyone inside the target group is not over 50K. So this is related to one notion in fairness called equalized opportunity. You probably know that fairness is a very complicated issue. So it's more of a proof of concept work, but you'll see, at least in some way, the logistic regression result has an undesirable, or it could be undesirable property in this data set. And so imagine you didn't know our result. Well, you can also fit a random forest or some other more powerful classifier, and you'll see it's actually much more robust to this attack. So it doesn't change its accuracy on the target group when you modify outside the target group. So you might incorrectly think that, oh, like you have to use improper learning. Like when I am creating this kind of per group noise, like it's just, there's no half space at all that is both accurate overall and behaves well in the target group. And like you would have no way to know this except that, we can run our algorithm and we see it's not the case. Like, so actually there is a half space which has just as good overall accuracy and does not horribly distort the false positive rate on the target group. Another thing you could try is like, oh, just do logistic regression and don't show me the, like if I'm going to do an ethnicity-based attack, don't show me information about ethnicity or gender or so on. Yeah, it turns out actually none of those things, they do make logistic regression better, but they don't fix the problem. So yeah, there's not an obvious way to get these good half spaces out of the classical logistic regression algorithm. Yeah, so this could be an interesting tool. I could say more about, there's some interesting related things people considered in fairness, but let me not in the interest of time. So that's the whole talk. Thanks for listening to me blabber on.
Thanks, Fred. Okay, I'll kill the recording so we can just like discuss and until we like to. Let's see.